All right, we're starting now. And we're going to be looking at question 8 for a start. And here is the question 8. And question 8 is about circle geometry. PON is a diameter of the circle. This PON is its diameter of the circle centered at O. TM is a tangent to the circle at M. So we have that TM is a tangent to the circle at the point M, a point on the circle. We can see that M is a point on the circle. R is another point on the circle such that OR is parallel to PM. Here is OR parallel to PM. Okay, the examiner showed the parallel lines there. And N and M, NR and MN are drawn. Okay, let's look at NR. Okay, here is NR, and then MN are drawn. Okay, so we draw NR and we draw MN. We draw NR and we draw MN. Okay, very good. Right, so we proceed to say we let angle M1 be 66 degrees, and there it is, it has been shown there. Okay, let's look at the questions. Give with reasons the size of each of the following angles. Now, the size of the angles required here, what size of the angles? Okay, the size of the angles, for instance, calculate with reasons the size of each. Oh, what time did we start today? First, things first. You know the time, Karabo?
So it's 8:38.
Yeah, okay, it's 8:38 p.m. Thank you for noting that. So this is the time at which we started. So our start is at that time. All right. We calculate with reasons the size of each of the following angles, the size of the angle P. Okay, we are interested in the size of this angle there. Right, so what is the size of that angle there? So we first realized that the angle P is actually equal to the angle M1. Angle M1 is equals to the angle P. So angle P is equal to angle M1, and the angle M1 is 66 degrees. What is the reason? It's because of the 10 chord theorem. So that is the thing. So this equals that one. M2, angle M2. Right, so at this point you realize that angle M2 needs to be determined. And what is the value of the angle M2? So we realize that angle M2 is here, but it's an angle subtended by a line, a chord that passes through the center of the circle and is called a diameter. A diameter will always subtend an angle of 90 degrees at circumference, because this angle M is an angle at circumference subtended by a chord through the center, and the chord is called a diameter. So in other words, angle M2 is 90 degrees. Why is angle M2 90 degrees? Because we say it is an angle in semicircle. The next thing is we are interested in angle N1. And here is angle N1. What is the size of the angle N1? All right, so we already know this one is 66 degrees, and we already know this one is 90 degrees. So we can get angle N1 is the third angle in the triangle. So to get N1, we can just simply say 180 degrees minus these other two angles. Okay, because it is the third angle in the triangle there. So angle N1 is basically equal to 180 degrees minus the other two angles in the triangle. So it's minus 90 degrees, the angle in semicircle, and also the 66 there. And the answer to this is it is 24 degrees. Why? Because it is the sum of angles, of triangle M and P. The sum of angles of triangle M and P. There, M and P. The sum of angles of triangle M and P. Now O2, angle O2, it's this one here. Right, obviously we see the relationship between this one and the angle P. So we can see therefore that angle O2 is equals to angle P. Angle O2 is equals to angle P and is equal to 66 degrees. Why? Because you are dealing with the corresponding angles. The corresponding angles occur when they're parallel lines. What lines are parallel that are making the angles O2 and P? The lines are actually in lines PM and what? Lines PM and OR. PM and OR. PM. To OR. Okay. So we did that one. And then we have one more, 8.1.5. We're interested in finding the size of the angle N2. How to find the size of the angle N2? All right. So we already know angle N1. We found angle N1, and we found angle N1 to be what? To be 24 degrees. So we just need to find angle N2 in here. What is the size of that angle there? Right, so we can actually be in a position to do this question. We can actually work in triangle RNO. So to do the question 8.1.5, we take angle R plus angle N1 plus angle N2, and it is the angle R plus N1 and 2. Okay, we already know that this angle O2 is already 66 degrees. So which means that if I add these ones here, I'm gonna get 180 degrees minus the 66 degrees. Okay, so if you're adding the two angles, you can say 180 minus the third angle. Why is this the case? Because this is the case because we're dealing with the sum. We're dealing with the sum of angles of triangle R and O. Now, angle R is actually equal to, this angle R is actually equal to N1 and N2 because this equals this, they are radii drawn from the center. So in other words, these angles are equal, and if they're equal, we actually can therefore say it is 114 divided by 2 because their sum is 114. And then 114 divided by 2 is actually 57 degrees. Why? Angles opposite equal radii. So this one here, the reason for this would be that angles opposite equal radii. Okay, we're good. So, and this cements, therefore, the fact that angle R is 57 degrees, and this angle is also 57 degrees. So, what is the examiner looking for? He's looking for the angle N2. So N1 plus N2, we've already said it's 57 degrees, but we already know the angle N1. Right, we call the angle N1 to be what? To be 24 degrees. So angle N1 is 24 degrees plus angle N2, which is 57 degrees. And what is therefore angle N2? It is 57 minus 24, 33 degrees. 33 degrees. Okay, so angle N2 is 33.
So how did you get to 24 degrees?
Okay, that's a good question. How did you get the 24 degrees? We got the 24 degrees in one question above. We got the 24 degrees in question 8.1.3 here. How did we get that one for the size of the angle N1? Because we in 8.1.3, we had to find the size of the angle N1. So we were facing this situation, did not know anything, and we looked at this shape, and we're supposed to find the size of the angle N1. And we realized that, okay, we knew something, okay? We knew that this is 90. So we actually looked at the triangle, this one here. And then we already know this one is 66 and this one is what? Is 90, so it's easy to get the third one. So we realized in 8.1.3 that angle N1 actually will just be 180 degrees minus the other two angles. 180 degrees minus 90 degrees plus 66 degrees. So, and now if you subtract here, why? Obviously, the reason for 180 minus is because of the sum of angles of triangle MNP. And this is 24 degrees and this is angle N1. Okay, that's how we got 24, and then we put the 24 here. And then we can get that angle N2 is 33 degrees there. Okay, so we're done with the question, and therefore that angle N2 is 33 degrees. We've done all the questions there. All right, so we're done with that question, the 8.1. And we're looking at question 8.2 right now. In the diagram, you have triangle AGH and triangle AGH. So there's A there, and then there's G there, and there's H, okay? So with those 3 points is drawn. F and C are points on A, G, and AH respectively. So you have F and C. They are points on A, G, and AH respectively, such that AF is 20 units, okay? AF is 20 units, there it is. Here is AF, and we can see the 20 units there. FG is 15 units, so with FG it is exactly 15 units. CH is 21 units, so we can see that CH is 21 units. There is a point on FC. There is a point on FC such that ABCD is a rectangle. A, B, okay, C, D is a rectangle. So, right, so D is a point on FC, okay, such that ABCD is a rectangle with AB parallel to GH. Okay, we have AB parallel to what? Parallel to GH. Okay, we have these parallel there. Obviously, if we have that ABCD is the rectangle, ABCD is the rectangle, so the interior angles themselves have 90-degree sizes. Right. With AB also parallel to GH. AB also parallel to what? to GH. Okay, you can see they're parallel there. The diagonals of ABCD intersect at M, and the diagonals of ABCD intersect at M. So at this point, we are looking at the diagonals of ABCD. They intersect at the point M. Okay, so obviously, one thing that's very important with a rectangle is a parallelogram. Okay, it's just a special form of a parallelogram. Right, so it means therefore these bisect each other. These diagonals will most certainly bisect each other anyway. Okay, so they bisect each other there. Okay, now something very important. Right, the diagonals intersect at M, a point on AH. Obviously, you can see that the point M here is on AH there. Okay, that is true. Explain why FC is parallel to GH. You need to explain why FC is parallel to GH. Why? Why?
So
why?
Proportionality.
Yes, I'm happy that you're bringing that point up there. So it's because of the fact that at this point, if you look at that is 8 point, we're looking at 8.2.1. So in 8.2.1, obviously we realize that obviously you're on point. We realize that FC itself is parallel to what? Is parallel to AB. We realize that FC itself is parallel to AB because it was given, well, not quite given, because we're given that AB is parallel to what? To GH. But we know that FC, which is this one, is parallel to what? Is parallel to AB, okay? But it's also parallel to an AB is parallel to what? AB is parallel to GH. So those three lines involved. And why are these the case? Because they're basically opposite sides of a rectangle. So we have opposite sides. Opposite sides of rectangle. Okay, opposite sides of rectangle. Right, because obviously this is a rectangle, so the opposite sides are parallel. That's why AB is parallel to what? To FC, or FC is parallel to AB. And then obviously, but because the examiner is saying, explain why FC is parallel to GH, why FC itself is parallel to GH. Right, obviously the reason is that first and foremost, FC itself is parallel to what? Is parallel to AB. Because the opposite sides of this rectangle here. And then we know that AB is parallel to GH. Why is AB parallel to GH? Because it was given, you know. So AB parallel to GH, it was given. Okay. AB parallel to AB is parallel to GH, it was given. So AB parallel to GH, which is given there. All right. We're good. The diagram has become a bit untidy, so let me clean it up. We continue. Right, calculate with reasons the length of what? Calculate with reasons the length of DM. The length of DM. We need the length of DM. We need to calculate that one with reasons and how many marks we're given there. Full 5. So if you get that one, it's very good. So you'll be just close to just getting the distinction there. So I'm going to do that question here. 8.2.2, closer to the diagram so that we're able to see exactly the diagram. Okay. At this point, right, so we have that, so we want to find dm. Want to find dm there. And to find dm, we have AC. First and foremost, realize that AC itself over CH. So AC over CH is equal to AF over FC, over FG, excuse me. So AC over CH is equal to AF over FG. Okay, why is this the case? Because of line parallel one side of triangle. Right. Or if you don't want to say that, it's true because of the proportionality theorem. Proportionality theorem. The proportionality theorem applies because FC is parallel to GH. Because FC, okay. Because FC is parallel to GH. You're still with me, Karabo, right?
Yes, sir.
All right, sorry. I thought maybe you gone because there was just an interfering call here. All right, so we continue. So calculate the reasons the length of dm. So we're interested in the length of dm. So then we have AC over CH. Right, so what is CH? CH is 21 units, so we put 21 here. And then we have AF. AF is 20 units, so you put 20 here. And then we have FG, which is what? 15 units. Right, so we just need to find AC. So which means AC is the same as what? Is the same as 20 times 21, you cross multiply. We divide everything by 15, and therefore AC is equal to what? It's equal to 28. With that said, it means dB is equal to, okay, so, right. So in other words, at this point, dB, so this is D, right? And then this is B, is equal to AC, the diagonals of a rectangle. So dB is equal to AC because they're diagonals of a rectangle. Okay, so now it follows therefore from this that dm, which is what they want, is actually half. It follows therefore that dm is equal to half dB. dm is equal to half dB. So here is dm. It is actually half dB. It's only half of the dB there. Okay. And now, which is half? What is dB? dB is 28 as well. So it's 28, which is equal to AC. So this is 14. units. So dm is 14 units. Why is dm equal to 14 units? Why is dm equal to half of db? dm is half of db. All right. Why? Well, the reason is that the diagonals of a rectangle, bisect. Diagonals of a rectangle bisect. Okay, so we found the length of dm to be 14 units. To be 14 units. And we're done. Goodness. We're done with these two guys. We're done. And we're happy. Well, here's question 9, very nice and easy. Okay, some theorem. There. So in the diagram, you have that JKLM is a cyclic quadrilateral, and the circle has center M. Prove the theorem which states that J plus L is 180 degrees. So we continue then. All right. So now what we're then getting, so we continue. We continue right now. Right, we need to prove that J plus L is actually 180 degrees. Okay, we have lots of space here, so we're going to use that. Okay, so we continue. So to do this one, we first perform a construction. The construction goes as follows. So you proceed to draw KO and MO. All right. So you continue. After this construction, we then do this one, which is, we call it O1. And then we also have this one, this angle, and we call it angle O2. Right, so if you look at the proof, angle O1 is twice J. Angle O1 is twice J. Why is angle O1 twice J? Because angle at center is equal to twice angle at circumference. And then now we also have angle O2. Angle O2 is twice L. This one. Angle at center, because O is the center, is twice angle at circumference. And then now angle O1 and O2 when added together is 360 degrees. And this means these are angles around a point. And now this means that angle O1 we can substitute here. In the place of angle O1, we know it's twice J. O2 is twice L, and this is 360 degrees. We can factor out 2 here, and then have angle J plus angle L is actually equal to 360 degrees. Right, so that's what we get. So it's equal to 360 degrees. So at this point, that means angle J plus angle L so J plus L is actually equal to 360 degrees divided by 2. Right, so divide by 2 both left and right. So angle J plus angle L, 360 divided by 2 is 180 degrees. And this is what had to be shown. All right, so we had to prove that angle J plus angle L is 180 degrees. And we can see that angle J plus L is actually 180 degrees. Okay, so we continue. All right, we continue. Right, we'll do the next question now. All right. All right, we continue with the next question. All right, so J plus L is 180 degrees. Okay, look at 9.2 right now. In the diagram, is a smaller circle ABTS, ABTS. All right, and a bigger circle BDRT. So there's BDRT, the bigger one, and this is a smaller one, are given. BT is a common chord. BT is a common chord. Straight lines STD. STD. And ATR. And ATR are drawn. All right. Okay. Now, chords AS and DR. Chords AS and DR. chords AS and DR. Here is AS and these DR. Are produced to meet at C. Okay, they meet at C there. They point outside the two circles. Outside the two circles. BS and BD are drawn. BS and BD are drawn. Angle A is equal to X. Okay, we can see angle A is X there. And angle R1 is Y. R1 is Y. We answer the questions below afterwards. Name giving a reason, another angle equal to X. Name giving a reason, another angle equal to X. Okay, where is X? X is this one. What other angle is actually equal to X? So another angle equal to X is what? Is the angle B1 because of this theorem here. So if you have this, you have this and that. This angle here is equal to this angle there, and the angles in the same segment. So we then say B1 is indeed equals to X because of the angles in the same segment. So which means therefore the answer here would be that B1 is equal to X, and the reason is the angles in same segment. Then you have Y. Y. Another angle equal to Y. Y first is this one. What other angle is equal to Y? Okay, so Y is equal to B2. This B2 is equal to Y because this is a cyclic quad. So the exterior angle of a cyclic quad. How do we see that? So we see it like this. Okay, if this is a cyclic quad, the vertices lie on the circumference of the circle, the boundary of the circle, then an angle here is always equal to an angle there. Okay, and this is true for a cyclic quad. So the exterior angle equals the interior opposite angle. Okay. So now, what is angle equal to angle Y? We've already seen, therefore, that it is B2 that is equal to angle Y. And the reason is that we have the exterior angle of cyclic quad the exterior angle of cyclic quad. The exterior angle of cyclic quad equals the interior opposite angle. Okay, so you can see that here, because sometimes it doesn't quite look like that. So you see that it can be positioned like this and with that. So that becomes a cyclic quad there. And then this side is produced. Okay, same thing I've drawn. Yeah, so you have these equals that one. All right. Now, prove that SCDB is a cyclic quadrilateral. So if you look at the fact that SCBD is a cyclic quad, then to prove that SCD B is a cyclic quadrilateral. Okay, this is becoming untidy. Let me clean it up. Let me clean it up. Okay, let's look at how do we prove this. How do we prove this one? Okay, first things first, we realize that the angle C, this one here, the angle C, this one, and the X and the Y in triangle ACR, in triangle ACR, this one is X and this one is Y, so we can be able to get the angle C, which means therefore, first to realize that the angle C is actually equal to 180 degrees minus the other two angles. Sum of angles of triangle ACR. So that is 9.22. So angle C is 180 degrees minus X, and it's into X plus Y. And so the reason for this is the sum of angles of triangle ACR. Okay, so we have got that. Then we have the next thing now. Angle SBD. Angle SBD. Angle SBD. This one here. And then if we add it with angle C, is equal to what? So that's what we're gonna do. So we're gonna say angle SBD right, so we have angle SBD. So now we have angle SBD. Angle SBD plus angle C is equal to what? Okay. Right. Now angle SBD, first and foremost, is actually B1. We saw that it is what? It is X, and we saw that B2 is Y. So the angle SBD is equal to the following. Okay, is equal to the following. So right, is equal to the following. So we proceed with the question. Right, so angle SBD is equal to X plus Y. So SBD is X plus Y. Then we add angle C, which is 180 degrees minus into X plus Y. Right, so what is all this? So it means therefore that angle SBD plus angle C, okay, the X plus Y minus that becomes 180 degrees in summation. We're in business now because we have proven that SBD plus C is 180 degrees. So we've proven that angle SBD plus angle C, if you add these opposite angles, you get 180 degrees in summation. If you add them up, get 180 degrees. Okay, get 180 degrees. So that is what is desired there. And now, if the opposite angles actually are supplementary, and the sum is 180, that is, so which means SC DB is a cyclic quad. It's a cyclic quad. Converse opposite Converse opposite angles of cyclic quad. Converse opposite angles of cyclic quad. Okay, this becomes converse opposite angles of a cyclic quad. Right. And there are many other ways to prove these results. So now the next question we shall do is 9.2.3. It is further given that D2 equals 30 degrees and AST is 100 degrees. D2 equals 30 degrees. Okay, let me clean the board up. The diagram has become quite untidy, so that you can be able to see clearly. It will help us. Nine point two point three. Right, if it is further given that D2 is 30 degrees. Right, where is D2? Here is D2, and it is further given that D2 is 30 degrees. What else is given? It is given that AST is 100 degrees. Angle AST, this one is 100 degrees. Okay, so we continue. All right, so if this is the case, what do they want us to do? Prove that SD is not a diameter of circle BDS, SD. Okay, prove that SD is not a diameter of circle BDS, right? It's not a diameter of circle BDS. So you have B, and then you have D, and then you have S. Right. So this SD here is not a diameter of the circle BDS. Okay, BDS. SD is not a diameter. Right, so there are a couple of ways, obviously, to prove that one. Yes, here we are to experiment there. So now we can first look at the fact that at this point, what we have is the following. This T4 relates to the exterior angle Y and this 30. So in grade 9, we were taught about the exterior angle of a triangle. Right, so 9.2.3. So first and foremost, we say that Y, so first we say T4 is equal to Y minus 30. Or you can say the exterior angle is equal to sum of the interior opposites, so which means Y is equal to T4 plus 30. So we're working in triangle TDR. So we say T4. Okay, I want to write a little bit more steps here so that you can understand. Because Y is equal to T4 plus 30. So we start by saying Y, T4 plus 30. Exterior angle of triangle equals interior opposite angle. Right, so you can say if you wish, best way to write in the exam, short reason. You can say exterior angle of triangle TDR is equal to the interior opposite. And the implication, therefore, is that T4 is equal to y minus 30 degrees. Okay. Next thing we need to do is to look at, so we have a statement about T4, but also we have also to look at the 100 degrees they've given us, okay? But first, the angle T1 is as follows, okay? The angle T1 is as follows. So the angle T1 is equal to the angle T4. They're vertically opposite angles. So, and the conclusion therefore from these is that angle T1 is also y minus 30 degrees. Why? Because these are vertically opposite angles equal. Vertical opposite angles equal. And so in triangle AST now, we can add all the angles there. In triangle AST. So let's look at triangle AST. Triangle AST, right? We have this angle here of 100 degrees. That one is X. And then we can add this one, which is y minus 30. Right, so we say y minus 30, which is angle T1, plus the angle X, which is up there. So this one is y minus 30, and then we add the X, and then we add the 100 degrees in the triangle, in triangle AST. So we have y minus 30 plus X plus what? 100 degrees. This is 180 degrees. Why? Sum of angles of triangle AST. The sum is supplementary sum. Okay, if you add everything here, you'll get that X plus Y is equal to 110 degrees. So X plus Y is 110 degrees. All right. And now X plus Y we remember that obviously it means it's X plus Y, but this is X and Y. So which means that X plus Y is 110 degrees. And that means SBD is 110 degrees. The angle, yes, the angle SBD is 110 degrees. And if SD were a diameter, it was going to subtend an angle of 90 degrees, but it is not the case. So This means SBD is 110 degrees. The conclusion, therefore, is that SD not diameter. SD not diameter. Line does not subtend 90-degree angle. SD is not a diameter. The line does not subtend 90-degree angle. Okay, there are many other ways to prove that. Okay, right. What is our time there, Karabo?
The time is 9:32.
9:32. And what time did we start? Need to check.
8:38, if I remember correctly.
Okay. Well done. Okay, good memory. Thanks for remembering correctly. Okay. And now it is 9:32. All right, so we have 6 more minutes, so we can still push. All right, so obviously we'll have the advantage to watch these intro. So we've answered this question on riders. These questions are under something we call the graded sets of riders. What are riders? Combinations of geometry theorems there in one figure, one diagram. Right, here is one more question, question 10. In the diagram, ABCD is a slightly quadrilateral such that AC is perpendicular to CB. So here is AC perpendicular to CB, perpendicular there. And DC is equal to CB. DC is equal to CB. AD is produced to M. AD is produced to what? To M. Such that AM is perpendicular to MC. AM is perpendicular to MC. You can see the perpendicularity there. Let angle B be X. So let angle B be X there. Okay, we're dealing with ABCD as a cyclic quad. So ABCD is a cyclic quad, all of whose vertices clearly lie on the circumference of the circle. Okay, I'm trying to remove writings there so that you can have a clearer diagram. Okay, right. You need to prove that. MC is a tangent to the circle at C. Right. So to prove that MC is a tangent to the circle at C, we proceed like this. We proceed like this. Right. So if MC is a tangent to the circle at C, we proceed like this. We realize that angle A2, right, so realize that, so this is how we're gonna do question 10.1.1. We realize that angle A2 is equal to angle A1. Angle A2 is equal to angle A1, and it is equal to what? Okay, this angle is 90 degrees minus X. Why? Because if you add all of them, you must get 180 degrees. So if you say 90 minus X, this and that, if you add them up, they will give you 90. 90 plus 90 is 180 degrees. But obviously, they are marked like this. Okay. Equal chords subtend equal angles at circumference. So these chords are equal, so they subtend 90 degrees minus X. So MC is a tangent to the circle at C. So A2 equals A1 equals 90 degrees minus x. So equal chords subtend equal angles. Okay, that's why we're saying angle A2 is equal to angle A1. But also now angle D2 is equal to x. Realize that angle D2 is equal to x, exterior angle of cyclic quad. Because if you have this here, this angle is equal to this. Right, so it's exactly the same situation. So D2 is equal to x, right? So we can see that angle D2 is equal to x. Why is it equal to x? Because we have the exterior angle of cyclic quad okay, D2 is equal to x. So D2 is x. But also we can see that with this, then it means angle C2 in this diagram will be 90 degrees minus x, because this is 90 degrees, and then if this one is 90 degrees minus x, you add all of them, you get 180. But it's 90 degrees minus x. If you add all of them, 90 degrees minus x plus x is 90, 90 plus 90 in the triangle DMC. You have 180 degrees if you add all the interior angles of that triangle. So we see that angle C2 therefore is 90 degrees minus x. Angle C2 is 90 degrees minus x. Why? Because of the sum of interior, the sum of angles of triangle DCM. Now we have C2 is 90 minus x, but also A1 is also 90 minus x. So the conclusion, therefore, is that angle C2 is equal to angle A1, which is equal to 90 degrees minus x. That is the conclusion. Therefore, C2 is equal to A1, which is 90 degrees minus x. And moreover, and the conclusion, therefore, is that MC is a tangent to the circle at C, because now if this one is a tangent, obviously it means this angle M2 is equal to that angle there. But we can see 90 degrees minus x there, and 90 degrees minus x equals to 2. So which means that MC indeed is a tangent to the circle at C. Okay. The conclusion is that therefore MC is a tangent to the circle at C. Okay, and obviously this is actually the converse 10-chord theorem. Converse 10-chord theorem. Converse 10-chord theorem. Okay. So we are good. We are really good. So the next question we're gonna do is, so we have proven that on 5 marks. We're gonna do this one. We need to prove that triangle ACB is similar to triangle CMD. Right, so okay, so continue. Yes. All right. So continue with that one. 10.1.2. 10.1.2. Right. So in 10.1.2, we do the following. We can do it even here in this small space here. Right, so we're looking at 10.1.2. So at this point, we're gonna work in triangle ACB and triangle CMD. So you tell the examiner, in triangle ACB and triangle CMD. So in triangle ACB and CMD. All right, we can see that angle B is equal to angle B is equal to D2 and it's equal to X. Okay, the exterior angle of a cyclic quad. So obviously we proved that exterior angle of a cyclic quad. Right, so at this point, angle B is equals to angle D2 exterior angle of cyclic quad. Moreover, if this D2 equals B, but also we have that angle A2 is equal to, excuse me, I mean angle A2 is equal to angle C2 because this is 90 degrees minus X, we've proven that. And also this is 90 degrees minus X. So, which means that angle A2 is equal to angle C2, and this is 90 degrees minus X. Why? It was proved, or basically it's the sum of angles in triangle. Okay. So this is like part 1, part 2. So now, okay, look, we are effectively looking at the angle, a triangle ACB. So here is A, C, B. So if you look at the triangle ACB and you draw it like this, ACB. Right, so this is A and this is C and this is B. 90 degrees. So this one is 90 degrees minus X. X. So, you still with me, Karabo, right? Okay.
Yes, sir.
Right. So, okay, fine, thanks. Right, you can see that we're looking at triangle ACB. So this one is 90 degrees minus X. This one is X and this one is 90 degrees. Okay, because these things are coming in the exam in the coming term. So it's very important that you master them because they're gonna come like in a dream. And you need to make sure that you excel, you know? So we have ACB, okay? And then now ACB has like A2 inside here as well. And then we have CMD, okay? So you have CMD. So CMD is like this. Trying to draw them separately. And now drawing them separately allows us to mark the angles and see them properly. This is C2, but it is 90 degrees minus X. 90 degrees here. This one is X, D2. So we've already seen that angle B is equal to D2 equals X. Okay, exterior angle of cyclic quad there. Next, we have already seen that A2 is equal to C2, which is, and this C2 is 90 degrees minus X as well. This C2. Right, someone gets a triangle. And then we can see clearly that, so we've seen that angle B is equal to D2. And we've seen that angle A2 is equal to angle C2. And then we can therefore see that angle C is equal to angle M equals 90 degrees. Okay, that is true, but it was just given anyway. Or we can say is the third angle in the third angle in the triangles. Third angle in the triangles. Okay. Now with this, so it means therefore the conclusion therefore is that therefore the triangle ACB is effectively similar to triangle CMD. Why? Because of angle. Okay, similarity is because of equiangularity, so the triangles must be equiangular with equal angles. Okay, so if the triangles are equiangular, equal angles, then we say the triangles are similar. Okay, so at this point, we're supposed to prove this one for 3 marks, and we've proven that for 3 marks there. Okay, please check the time again there, Garabo.
So the time is 9:48.
9:48. Okay, let me check. All right. Remember recording this lesson as well. So it is 9:48. Okay, that's fine. We've exceeded by 10 minutes. And it's okay. So I'm going to record the lesson. Once again, the lesson was recorded, so I'm going to send you this. Yeah, I'm planning to send it today evening. Yesterday's one, there was load shedding at night.
Oh, no problem, sir.
Yeah, so load shedding, I hope load shedding is not going to happen now, because it takes a bit of time, like sometimes 15 minutes or more. And then yesterday when I was busy uploading it around 10, power went. And then when the electricity went, the video could not be uploaded. So I had to do it today. Because throughout the night, then, the power came back late again at night. So I had wanted to do it immediately, but even today, because now it's like 9:49. So I'm hoping that the power is not gonna go. I'm just looking at the schedule now. I'm hoping the power is not gonna go at 10. It might just be going at 10. You see,
okay,
it's gonna go now in 10 minutes. Okay, it's gonna go now in 10 minutes and come back at 12 midnight. It means therefore I'm gonna try and send it, but first the system must save the video in the cloud. After saving this video in the cloud, that's when I can take it and upload it on YouTube for you to be able to watch. Sorry, I will see if it is going to work, but 10 minutes is way too short. It takes a bit of time for this video to be uploaded. But yeah, I will send you the link as soon as I upload it. Okay.
Okay, sir.
All right, thanks a lot, Karabo. Yeah, my power is just going to leave in the next 10 minutes. So I'm going to see you again. We'll talk, but yeah, soon, because tomorrow we said we have a break. Okay.
Yes, sir.
Yeah, we'll break tomorrow. Yeah, we'll talk then, because obviously we potentially need to use Wednesdays, Thursdays, and Fridays. Yeah, but you can do more days, so I'm going to check with you from time to time. Okay.
Yes, sir.
Before schools reopen, when the schools reopen, we get back to 2 days a week. Yes, the normal 2 days a week when you guys are back at school. So thanks, Karabo. Have a good evening. Okay.
Okay, bye, sir.
Thanks. Goodbye, Karabo. Goodbye.